When we hear the phrase quantitative methods, we usually think of numbers, statistics, surveys, experiments, graphs, and mathematical models. When we hear the word philosophy, we tend to think of something quite different: abstract questions about reality, knowledge, truth, morality, and human existence. At first glance, these might seem like two very different intellectual worlds, but they are much more closely connected than they appear. Every time a researcher measures something, chooses a variable, constructs a statistical model, or decides that a particular result counts as evidence, philosophical assumptions are already at work. What exactly are we measuring? Does the number really represent the phenomenon we care about? What can a statistical relationship tell us about causation? And perhaps most importantly, does turning something into a number necessarily help us understand it? These questions take us directly into the philosophy of science. In this video, we'll explore the relationship between quantitative methods and philosophy, from ancient mathematics and the scientific revolution to statistics, social science, artificial intelligence, and big data. And we'll see that quantitative methods are not simply technical tools. They are also ways of thinking about reality. The relationship between philosophy and quantification goes back thousands of years. The ancient Pythagoreans believed that number was fundamental to reality itself. Mathematics was not simply a convenient way of describing the world. Numerical relationships revealed something about the underlying structure of existence. Plato also gave mathematics a privileged position. For Plato, the physical world was changing and imperfect, while mathematical truths seemed stable and universal. Geometry therefore offered a model of genuine knowledge. Aristotle was more empirical. He emphasized observation, classification, and the systematic study of nature. But he also contributed to the idea that knowledge could be organized rationally and systematically. The relationship between mathematics and science became much stronger during the scientific revolution. Galileo famously argued that nature could be understood through mathematics. Instead of merely describing how objects moved, scientists could measure their motion. How far, how fast, at what rate of acceleration. Descartes similarly dreamed of a universal science grounded in mathematical reasoning. And then Newton demonstrated just how powerful this approach could be. With a relatively small number of mathematical laws, Newton could explain the motion of falling objects, projectiles, planets, and moons. This achievement had enormous philosophical consequences. If mathematics could reveal the laws governing the heavens, perhaps quantitative methods could reveal laws governing other areas of reality as well. Eventually, this ambition would extend beyond physics and into biology, economics, psychology, sociology, and political science. By the 19th century, thinkers such as Auguste Comte argued that the study of society should become genuinely scientific. Comte's positivism held that reliable knowledge should be grounded in observation and empirical regularities rather than metaphysical speculation. Society itself could therefore become an object of scientific investigation. Researchers could collect data on populations, crime, poverty, education, economic activity, political behavior, and many other aspects of social life. This ambition became increasingly important in the 20th century. Logical positivists attempted to connect meaningful scientific claims with observable evidence. Although logical positivism eventually faced serious philosophical difficulties, its influence helped strengthen the idea that scientific concepts should have clear empirical connections. Karl Popper rejected the positivist emphasis on verification. For Popper, we can never conclusively verify a universal scientific theory. No matter how many white swans we observe, for example, we cannot logically prove that all swans are white. But one black swan can falsify the claim. Popper therefore argued that scientific theories should make precise claims that expose themselves to possible refutation. Quantitative methods fit naturally into this vision because precise predictions can often be tested against numerical evidence. But this raises an important question. Where do the numbers themselves come from? Imagine that I tell you that one person weighs 80 kilograms. There is relatively little mystery about what that number represents. But now imagine that I tell you someone has an intelligence score of 120, or a happiness score of 8.2, or that a country has a democracy score of 7.5. Suddenly things become more complicated. What exactly has been measured? This is one of the central philosophical problems underlying quantitative research. Measurement is not simply finding numbers in the world. Researchers have to decide what concepts mean and how those concepts will be represented numerically. Consider something like political trust. Political trust is not sitting somewhere waiting to be placed on a scale. Researchers might ask people how much they trust parliament, the courts, politicians, or government institutions. Responses can then be converted into numerical variables. But does that variable really measure political trust? Perhaps it measures satisfaction with the current government. Perhaps respondents interpret the question differently. Perhaps the concept of trust itself varies across cultures. These are questions of construct validity. And construct validity is not merely a statistical problem. It is a philosophical problem about the relationship between concepts and reality. This becomes especially important in the social sciences, where researchers routinely quantify concepts such as inequality, prejudice, democracy, social class, well-being, political ideology, and quality of life. The numbers may look precise, but numerical precision does not automatically produce conceptual precision. Another major philosophical issue underlying quantitative research is the problem of induction. David Hume pointed out that much of human knowledge involves moving from observations of the past to expectations about things we have not yet observed. Suppose we conduct a survey of 2,000 voters. We are rarely interested only in those 2,000 people. We want to say something about millions of voters. That means moving from a sample to a population. Statistics provide sophisticated methods for doing this. But statistics does not eliminate the philosophical problem. It manages uncertainty. Different statistical traditions also interpret uncertainty differently. In frequentist statistics, probability is generally associated with long-run frequencies and the behavior of procedures across repeated samples. This tradition gives us familiar tools such as hypothesis tests, confidence intervals, and p-values. Bayesian statistics approaches the problem differently. Bayesian methods allow researchers to represent uncertainty through probabilities and update those probabilities as new evidence becomes available. Neither approach is philosophically neutral. They embody different ideas about probability, evidence, uncertainty, and what conclusions data can justify. This is why debates over statistics are sometimes surprisingly philosophical. When researchers argue about whether a p-value provides strong evidence, they are not simply arguing about mathematics. They are arguing about what evidence means. Quantitative methods also involve questions of ontology. Ontology asks, what kinds of things exist? Some phenomena seem naturally measurable: length, mass, temperature, reaction time. But what about intelligence, happiness, racism, social class, political polarization, human dignity? These concepts are real in important senses, but their relationship with numerical measurement is much more complicated. The danger is that once something has been assigned a number, we can begin treating the number as though it is the phenomenon. But the measure and the thing being measured are not necessarily identical. GDP, for example, measures economic production. It does not directly measure human flourishing. A country can experience rising GDP while also experiencing increasing inequality, environmental degradation, or declining social well-being. The philosophical lesson is simple but important. What we choose to measure influences what we are able to see, and what we fail to measure can become practically invisible. Quantitative research also depends heavily on models. A statistical model simplifies reality. Economists model markets. Political scientists model voting behavior. Epidemiologists model disease transmission. Climate scientists model future temperatures. Psychologists model human behavior. But what exactly is a model? Does a successful model reveal the actual structure of reality? Scientific realists tend to argue that successful scientific theories and models provide at least approximately true descriptions of an independently existing world. Instrumentalists are more cautious. For them, a model may be valuable primarily because it helps us predict, organize observations, or solve problems. It does not necessarily have to provide a literally true description of reality. This debate has become especially interesting with the rise of machine learning. Some artificial intelligence systems can make remarkably accurate predictions while remaining extremely difficult to interpret. A model might accurately predict who is likely to default on a loan, develop a disease, or leave a company, but it may not clearly explain why. This creates an important philosophical distinction between prediction and explanation. Knowing that something will happen is not necessarily the same as understanding why it happens. Philosophers have also challenged the idea that everything important can be understood quantitatively. Hermeneutic thinkers emphasize interpretation and meaning. In the social sciences, this distinction is sometimes expressed through the German concepts of Erklären and Verstehen. Erklären refers roughly to causal explanation. Verstehen refers to interpretive understanding. Suppose statistics show that unemployment strongly predicts support for a particular political movement. That is useful information. But it may not tell us what unemployment means to the people involved. Does it produce anger, loss of identity, economic insecurity, distrust of institutions, a sense of humiliation? Understanding these experiences may require interviews, historical analysis, ethnography, or other qualitative methods. This does not mean quantitative research is inferior. It means different methods answer different kinds of questions. Feminist philosophers of science and standpoint theorists have added another important criticism. Data are not simply collected from nowhere. Researchers decide what questions to ask, which populations to study, which categories to use. These decisions can contain social and cultural assumptions. So even a perfectly calculated statistical model can reproduce questionable assumptions built into the research design. Recent debates in psychology, medicine, economics, and other fields have made these philosophical issues especially visible. The so-called replication crisis revealed that some published findings could not be reliably reproduced. One problem involved excessive dependence on statistical significance. A result with a p-value below 0.05 might be labeled statistically significant. But statistical significance does not necessarily mean the result is large or important. Researchers therefore increasingly emphasize effect sizes, confidence intervals, pre-registration, replication, robustness checks, and transparent research practices. The deeper philosophical lesson is that no statistical procedure can replace scientific judgment. Methods help us reason. They do not do the reasoning for us. This becomes even more important in the age of big data. Researchers now have access to data sets containing millions or sometimes billions of observations. Computers can identify patterns that would have been impossible for earlier generations of researchers to discover. But more data does not automatically solve old philosophical problems. Most importantly, correlation is not causation. Suppose two variables are strongly associated. Perhaps one causes the other. Perhaps the causal relationship runs in the opposite direction. Perhaps both are caused by a third variable. Or perhaps the relationship is partly accidental. Modern causal inference tries to address these problems using techniques such as randomized experiments, instrumental variables, difference in differences, counterfactual reasoning, and causal graphical models. But notice what happens here. To estimate causation, researchers must make assumptions about how the world works. Which variables cause which? What would have happened if the treatment had not occurred? Those are partly statistical questions, but they are also philosophical questions about causation. Interestingly, the relationship now works in the opposite direction as well. Philosophy increasingly uses quantitative methods. Experimental philosophy, sometimes called X-Phi, uses surveys and experiments to study people's philosophical intuitions. Instead of asking only what philosophers think, experimental philosophers investigate how ordinary people actually reason. Formal epistemology uses probability theory to analyze rational belief. Decision theory mathematically investigates how rational agents should choose under uncertainty. Philosophers of AI study fairness and privacy. So, quantitative methods are no longer simply something philosophers analyze from the outside. They have increasingly become part of philosophical practice itself. So, what should we conclude? Numbers are extraordinarily powerful. Quantification allows us to detect patterns that intuition alone would never reveal. Statistics allows us to reason systematically under uncertainty. Mathematical models allow us to represent complex systems and generate predictions. But numbers never completely speak for themselves. Behind every data set are decisions about what to measure. Behind every variable is a concept. Behind every statistical test is a theory of evidence. Behind every causal claim are assumptions about how the world works. And behind every model is a decision about which aspects of reality matter enough to include. That is why philosophy remains essential to quantitative research. Philosophy reminds us to ask, what exactly have we measured? What assumptions made this measurement possible? And what conclusions does the evidence actually justify? Quantitative methods help us count, compare, predict, and test. Philosophy asks what those numbers mean. And perhaps the best science emerges when we refuse to choose between the two. Because the ultimate goal of research is not simply to count the world, it is to understand it.